Alright, next we are on our list is the inverse Laplace transform. So as we have said earlier, we have that integration to compute the inverse Laplace transform, which helps us to compute from S domain to time domain, but we have already seen some of the Laplace transforms. Therefore, it will be much better to compute the inverse Laplace transform rather than going to that formal integration definition to do it using the basic Laplace transform of the functions we have seen so far. So in that case, when we are given any function, then it is better to convert it into these functions that we have already seen. And just to summarize, we have seen the Laplace transform of u at t as 1 over s. So any constant k multiplied by u at t would give us k over s. And we have seen the Laplace transform of Dirac delta to be 1. We have seen the Laplace transform of a ramp function t at u at t to have 1 over s squared. We have seen an exponential function e raised to minus at to have a Laplace transform of 1 over s plus a. And lastly, we saw the two trig functions cos omega t to have a Laplace transform of s over s squared plus omega squared, and sine omega t to have omega over s squared plus omega squared. These are the Laplace transform functions that we saw already. So the inverse Laplace transform uses these functions which we have already to compute the time domain of a function. So as an example, let's say we have a function g at s which is given by 7 over s minus 31 over s plus 7. So let's say this is a function in s domain, right, because of the s. So if we are asked to convert this function into a g at t, a time domain, then rather than taking this into the definition where it says 1 over 2j and integrating it into that sigma minus omega naught, sigma plus omega naught, rather than doing that, we would rather be better to convert these things using the functions that we have already been studying. So what do we have here? The Laplace transform of g at s has to be, using our linearity property, it has to be, or the inverse Laplace transform that also follows linearity. We can compute is at minus the inverse Laplace transform of 31 over s plus 7. So this is the same as if we take out the scaling, we have the Laplace inverse transform of 1 over s minus, if I take 31 out, then it will be the Laplace inverse transform of 1 over s plus 7. So what does that tell us? 7 times, we have already got that 1 over s as u at t. So this is 7 times u at t in time domain. So f at t is going to be 7u at t, because 1 over the Laplace inverse transform of 1 over s is u at t. So if Laplace transform works this way, if that's Laplace transform, then the inverse is the other way, right? So if 1 over s is the Laplace transform of u at t, that means u at t is the inverse Laplace transform of 1 over s. It's like arc sine and sine. Minus 31 times, what is this? S plus 7. What does that tell us? S plus 7 tells us that this is a Laplace transform of an exponential function where a has a value of 7, as we have seen here. Therefore, we have 31 times e raised to minus 7t u at t. So that's basically enough, or we can, because we have u at t there, 7 minus 31 e raised to minus 7t u at t. So that's the time domain function, and if we use Laplace transform, it should take us back here. So this is when we are given the Laplace transform in terms of two denominators like this, but it's not usually as pretty, because in some cases we might need to decompose a function. For example, say we have an inverse, say we have a function in time domain f at s equal to 2 times s plus 2 over s. So when we have a function like this, we need to decompose it into two or more functions which are easier to transform using our table already. By the way, I have included this table in your slides on the PowerPoint. So when we have a function like this, then it's advisable for us to decompose it into a better function. So if I take this function and multiply it, it will give me what? 2s plus 4 over s, right? So that is the same as 2s over s plus 4 over s. Now it is easier. This is the same as 2 plus 4 over s. So finding the Laplace transform of this function is much easier than finding that. So in this case we will find the inverse Laplace transform of 2 plus the inverse Laplace transform of 4 over s. As you have guessed it already, we have for 2, because it is just a function, we already have here for Dirac 1. So that is the same as 2 multiplied by the Laplace inverse transform of 1, right? Just to write it, plus the Laplace inverse transform 4 times the Laplace inverse transform of 1 over s. We already know that the Laplace inverse transform of 1 is Dirac delta, which means we have here 2 Dirac, 2 multiplied by the impulse function, plus 4 times what gives us 1 over s. As we have seen here already, 1 over s is a Laplace transform of u at t. So we have here 4 u at t. So this is the function that gives us the Laplace transform of this one. So that is Laplace transform, and from there that is inverse Laplace transform. Alright. But in some cases we are not going to have functions as easy, in which case we have to split them into partial fractions. For example, we know that when you are given a function, say v at s to equal 1 over s plus alpha and s plus beta. So when we are given a function like that, we have to be able to split this into partial fractions where we have s plus alpha plus beta over s plus, b over s plus beta. And if we are successful in decomposing this into the sum of two partial fractions, then finding the Laplace transform of that would be easy, right? So finding the inverse Laplace transform of v of s is going to be finding the inverse Laplace transform of a over s plus alpha plus the inverse Laplace transform of b over s plus beta. And that's easy. We have a and the inverse Laplace transform of 1 over s plus alpha, which we have already seen, plus b times the inverse Laplace transform of 1 over s plus beta. we know that if we have a here, that part is e raised to minus alpha t plus, in this case, the inverse Laplace transform of that guy here is e raised to minus beta t. Now the question is, still we haven't solved, sorry. Okay, yeah, sometimes this thing goes crazy. I touch things which I'm not supposed to, I think. Okay, now the question is, what is A and what is B? So we have to come up with a way to find from this, from 1 over s plus alpha, s plus beta, we have to come up to a way where we can find A such that the sum of these two is going to give us beta. And A is found by just solving the whole thing here, which is V at S. We have already defined this to be V at S. So multiplying V at S by S plus A, S plus alpha, and computing it for S equal to minus alpha, which is something that would make it 0. And B is equal to V at S multiplied by S plus beta, and then computing that for minus beta. So that's the partial fraction you must have covered in your algebra class or something. So using that, let's solve for functions. So let's say f at s equals, I think I can make this thing a little bit thicker. Okay, f at s is equal to 7s plus 5 over s squared plus s. Let's solve this. So we want this to be, we know that it is 7s plus 5 over s times s plus 1, right? I think I can make this thing a little bit thicker. Alright, so we want that to be the sum of s plus b over s plus 1. Because if we manage to do that, then finding the Laplace transform of a over s and the inverse Laplace transform, I should say, of a over s and b over s plus 1 would not be that difficult. So what would be A? A is going to be using that. A is going to be f of s multiplied by s, and solving that for s equal to 0, that's what makes it 0. So that would be 7s plus 5 over s times s plus 1 multiplied by s, and solving that for s equal to 0, which is, s would be cancelled out. We have 7s plus 5 over s plus 1 at s equal to 0, which would be, if we substitute 0 here, it will be 1 in the denominator, and here it will be 12. What about b? B would be f of s times s plus 1, right? So that it would cancel out for s equal to minus 1. So that would be 7s plus 5 over s times s plus 1 multiplied by s plus 1, and solving that for s minus 1. That should give us, that would cancel, and when s is minus 1, you will have here minus 7 plus 5, which is minus 2, and we have here minus, so s would be equal to 2, which means 7s plus 5 over s squared plus s can be decomposed into 12 over s plus 2 over s plus 1, in which case computing the Laplace inverse transform of f of s is going to be the Laplace inverse transform of 12 over s plus the Laplace inverse transform of 2 over s plus 1. So this is equal to 12 times the Laplace inverse transform of 1 over s plus 2 times the Laplace inverse transform of 1 over s plus 1. You already know the answer, right? 1 over s, if we go back to our table, you remember here 1 over s is u at s, and 1 over s plus a is e raised to minus 80. Therefore, here we have 12 multiplied by 1 over s is u at t, so that gives us u at t, plus here we have 2 times e raised to minus t u at t. So here we have 12 plus 2 e raised to minus t u at t. That will be the inverse Laplace transform of this function. So we have cases where these cases are called distinct poles. You see here we have seen in our previous chapter that whatever makes the denominator 0 are the poles. So in this case we have two distinct poles. We have a 0 pole here and we have a minus 1 pole. So these factors are distinct. So that is distinct poles method of residue. And so in this case we have the distinct poles where the two poles are different, and now we will see the repeated poles.